gonna have to add things. I'm gonna add on the margins on some blank spots, so make sure you fill in. It's very important when you review that it's there, okay? So, yeah, I was just, today there was that report, right? I don't know if you listened to the news, but that thanks to TikTok and all those social media apps out there, the attention span of people is shortening, right? Like TikTok, all short videos, right? So you just keep on going. And so I know that sometimes I go a lot longer than a TikTok video, right? And I just can't fit it in. I wish I could do it in 60 seconds, right? I can't. So I'm limited to that as well, that I need time to explain things, right? Anyways, so probability. We're going to talk about probability and odds. Those are like the main two categories in this unit. We're going to start with probability, and then we're going to move over to odds, and then we're going to go back and forth. Don't dread it. It's okay. It's going to be very doable. I'll show you how. But probability is the likelihood. Write this down. Likelihood of an event right? It will tell you the likelihood of the event happening. So rain, snow, a team winning the game, you getting COVID, you being admitted to ICU, right? Like those are all probabilities, right? And they base it on data that they've collected, right? So it's the likelihood of an event happening. It can be stated in three main forms. It can be stated as a percentage, as a fraction, or as a decimal or a number. Okay, so three main ways to express a probability. Fraction is the most common that you will see, but the other ones are there as well. What are odds? The main thing I want you to think of when you're thinking of odds would be favorable and against. Favorable and against. I don't know if you had junior high teachers that told you that odds can be stated as a fraction. It can be, but I will never do that. Okay, just to make sure we don't mix them up. Okay, so in this course, you state odds as a ratio. It's always going to be a ratio, and there's no total, right? What do you mean by that, Mr. Erickson? There should not be a total. Like if there's 10 people that are interviewed, a ratio would odds would never have 3 to 10, never. It'd be 3 to 7 because 10 is all together. Because if 3 like pepperoni, 7 do not like pepperoni. So it's 3 to 7. It's never out of 10, right? Like so, odds will never have the total there. Moving on. So this is just, if you flip this, right? If you go to this booklet, you're like, okay, odds, okay, got it. And now I can dive into the booklet, right? So it's just a bit of a bird's eye view of what we're doing here. And then we're going to start a little bit with reducing fractions. Not like, okay, reducing fractions is going to happen, but not very often. So you can probably score quite high on a test without knowing how to simplify. But if you want that high mark, you need to know how to simplify because it will be asked of you here and there. So let's go to experimental probability. So I want to give you some, in this section, you will simplify fractions, okay? What does simplify mean? You write in lowest terms, right? So if you have 9 over 15, right? That's not lowest terms because you can divide both of them by 3. So you get 9 divided by 3 is 3, 15 divided by 3 is 5. That would be writing the fraction in lowest terms. You need to divide both of them. You need to be able to divide both of them by the same number, and then you possibly arrive to the lowest possible term. Okay, that's what it means. And I'll give you 3 rules. Divisibility rules, we'll write that down. I'll zoom into that corner here. And so there are 3 main ones. There are more, but I need only 2. If last digit is even, right? So what does that mean? If the number ends in 0, 2, 4, 6, or 8, we divide by 2, okay? And you can keep dividing by 2 until it stops, right? You can keep dividing by 2. If it's even, keep doing it, eventually you'll get there. The next rule is if sum of digits is divisible by 3, then divide by 3. And I will make sense of that when I do examples, okay? Last rule, if last digit is 0 or 5, what am I going to divide by? Divide by 5, okay? So these are the 3 that I'm going to draw from for my examples. So if you have a big number, it ends at 0, 2, 4, right? 6, 8, divide by 2. Just keep dividing by 2. In no particular order. Whatever works, you get there. So here we go. Moving over to here. So this one, for example, they're not even, right? They don't end in 0, 2. You have got to be able to divide both of them by the same number. So this is what I do, watch. 3 and 9 is what? 3 and 9 add up to 12, right? Can I divide 12 by 3? You betcha, right? You can. Then you go 1 and 1 is 2, plus 7 is 9. Can you divide 9 by 3? Yes, you can. So you did that check, meaning I could divide both of them by 3. This is how I show the work, right? And then you grab your calculator, right? And you go 39 divided by 3. If you get a decimal, no go. You can't do it, right? You did something wrong, or you can't. Then you go 117 divided by 3. That's 39. And you might be tempted to say, I'm done. But I don't know if you see that 13 goes into both of them. There's no rule for that. You just got to be able to see that, right? So 13 divided by 13 is 1. 39 divided by 13 is 3. That's when you're done. Like you can't go any smaller than 1, right? So 1 over 3. Let's say you don't get it. You're like, I don't see it, Mr. Dixon. I can't see it. Watch this. This is the last resort. I go 39 divided by 117. Boom, right? Oops. 0.33. Oh, you should recognize that that's 1/3. And you reduce the fraction just like that, right? So I will accept that if you come up with it. Next, this one. I look at it and let me do it the long way. This is just a very long way of doing it, but then you get it for sure. They're both even. Divide both of them by 2. 32 divided by 2 is 16. 48 divided by 2 is 24. Make it smaller, right? They're still even, right? I will keep doing it. Divide by 2, divide by 2. I will continue here. 16 divided by 2 is 8. 24 divided by 2 is 12. And now you should probably see, oh, I know 4 goes into both of them. So I'll divide both of them by 4. That's 2 over 3. And then you're done. So some of you might do it a lot quicker. Some of you is like, yeah, I know that, I'll just divide everything by 16. Sure, if you know your mental math, if you're really good at it, if you remember your multiplication table, go to town. So there's longer ways of doing it, and there are quicker ways of doing it. No big deal. This is how you check for sure, though. If you divide 2 divided by 3, you better get the same if you were to divide 32 divided by 48. Like those two should match. You should get the exact same decimal if you were to do that. Okay. So keep that in mind. Let's keep going. And I want you to try it right here. Just do A and D right now. If you have time to do B and C, go for it. So on the back side, just do these two here. Simplify those two. And I'll meet you in a couple of minutes. So on 144, just A and D, try to reduce those, see what you get. And if you're done, all right. I don't know how you did this. This is my way of doing it. As long as you get to the same final answer, we're in business. I see that I can't divide both of them by 5, so that doesn't work. So I add them up and I get 9, and I get 9 as well. I can divide both of them by 3. So I go ahead and do that, and you get 15. 15 over 24. You should recognize that you can still divide both of them by 3. Right, so that gives you 5 over 8. And if you arrive to 5 over 8, you're good to go, right? I'm going to go to D here. You should recognize that both of them can be divided by 9, right? And so you get 6 and 9, and you're not done yet. You can divide both of them by 3. So you get 2 over 3, okay? So there's your reduced simplified fraction, just like that. I will do, just for fun, I'll do these ones here. So technically, they're both even. So I'm just going to go ahead and divide both of them by 2 right away. So that's 84 over 147. And then I'm kind of stuck. They're not both even. I add this up, it gives me 12. I add up this, and that gives me 12 as well, meaning that both of them are divisible by 3. That gives me 28 over 49. At that point, you should recognize that both of them can be divided by 7. And so that's 4 over 7 is your answer there. One more. Both of them end up in 5. So I'm going to go ahead and divide it by 5. So you got 135 over 315. They're still ending in 5. So I will keep going. And that gives me 27 over 63. Okay. And you're not quite done yet. What you can do there is divide them both by 3, or you divide them both by 9. So I'm going to divide this by 3 and this by 3, because this gives me 9 and this gives me 9, so I can do them both. That's 9 over 21. Divide them by 3 again. That's 3 over 7. And that's your answer. So again, it's not going to be all the time that I ask you to simplify, but it's definitely going to be there. So if you want to score, so let's say a question is worth 2 marks, you get 1 mark for the actual answer, and then simplifying maybe another mark or half a mark, depending on how much work is required. Okay. Now, we're gonna write this down making sure we understand the difference. So at the top of 144, you got that part, right? Write this down. There's going to be a bit of information there. When we're talking probability in this course, and actually in general, but nobody explicitly makes a distinction between the two, there's something that we call theoretical, and a different one that we call experimental. On 144 at the top, there are two different types of probability, and I will ask you in very clever ways. I will ask you, hey, give me the theoretical probability, and then give me the experimental probability. And it's going to be you understanding what's the difference between them. And this is just very, very simple terms. Theoretical tells you what should happen. In basic terms, theoretical will tell you what should happen. For example, if you're rolling a die, what's the probability of rolling a 1? 1 in 6, right? That in theory, that's what should happen. If I roll it twice, or let's say I roll it 6 times, I roll my die 6 times, do you think I'll get just 1 in those 6 rolls? Is there a chance that I got more than 1? Absolutely, right? What's the problem? You haven't rolled long enough. You have to do like 100 or 1,000 rolls to realize, wait a minute, that is actually happening in the long run. Okay, so what should happen? And experimental is what actually happened. Right? Experimental is what actually happened. And this is based on trials. So let's say you're in a lab performing trials, or you could poll people, right? Or you can do an experiment, etc. So always focus on what actually happened when it's the experimental. Theoretical is what should happen, right? And this is the sample size. Sample size. Okay, what is the sample size? Number of trials. Sorry, not two L's. Number of trials, experiments, etc. I'm trying to minimize the amount of writing, but some you need to write down. Sample size. If you have a small sample size versus a large sample size, it makes a difference. Okay? So if your sample size is small, something is going to be true. If you increase the sample size, or if you increase the number of people you ask, something else is going to be true. Ready for this? A small sample size. The theoretical will not be equal to the experimental. Okay? In the small scale, things are not going to pan out the way you're predicting it to be. But when you increase your sample size, then the theoretical, I will say this, disclaimer, is going to be very close to. So we do like a wave, two waves, not an equal sign. the theoretical will be close to the experimental. Performing more trials will increase accuracy between the two. Between, to shorten that, if you're in college or university, some profs are just going to just go through it and you're going to be like, wait, I'm not done, right? So you got to come up with clever ways to shorten words, right? Don't write down the whole thing word for word. I learned that lesson the hard way. And so this page right here, I hope that when you flip through it, that you're realizing there's two types of probability that we're talking about: theoretical, experimental. And then there's the sample size has a role in these two. Slowly they become closer, almost as if they're the same. But if the sample size is small, they're not going to be the same. Okay. So let me just give you a quick. It's not really going to help, but we're still going to see it. But that will stop blocking. So let's say you're doing number of rolls, right? And so you roll a die and you get a 1, a 5, a 4, a 6, a 1, and a 3, right? You just roll it, doing 6 times, right? So what's the probability? This is the experiment, right? You perform an experiment, you roll 6 times, and what's the probability of getting a 1 here? How many times did you get a 1? 2 out of 6, right? But in theory, I completely butchered that. But in theory, what's the probability of rolling a 1? Probability of rolling a 1 is 1 in 6. And you're like, Mr. Dixon, why are they different? You're saying in theory 1 in 6 will be a 1, but then you're saying 2 out of 3. Because you've only performed a small experiment. You need to roll 100, 200. I used to make students do this, by the way, but then a lot of students weren't too thrilled about it. But if you do 200, 300, 500 times, this number gets very close to that, and maybe even exactly that. So if you learn anything today is the sample size. Increasing the sample size will increase or make the results, your predictions more accurate. Okay? It's not like the theory doesn't work. In theory, that is what it is, right? Okay, let's keep going. 145 here. We're going to add to this chart, by the way. So we're just going to start. I need you to be able to do this, okay? You will need to convert between fractions, decimals, and percentages, okay? And I will say this, disclaimer, put this in your notes, right? A note, we state decimals to 4 places. Okay. And it's just going to make things easier for us. So if we state decimals, we want to use 4 places in this unit, okay? If applicable. So grab your calculator. The first is going to be easy. So I go from 1/5, I'm going to go from fraction to decimal. So basically all you do is 1 divided by 5. And in this case, there is just 1 decimal, so that's all you do. Okay? I think just follow along for now. Don't assume you know how to do it. I know you do, but there's little things that you need to watch out for. Then I'm going to go from my fraction to the percentage. So I go 1 divided by 5 times 100. Right? So I don't want you to go from the decimal to percentage. I want you to go back to the original, divide it like that, and then multiply it by 100. So it's 20%. Okay? If you want to score full marks, then this is how you do it. Next, if you have a 0 at the end as a decimal, you can just cancel it out. You can trailing zeros, you can slice them away. If they're in between, don't get rid of them. But so you go from here to there by just multiplying that by 100. So 0.7 times 100, 70%, right? Then I'm going to go back to the original, and this is maybe a refresher from, I don't know which grade this would have been, right? But this is how I do it. Write down the decimal, put that in your numerator, and you go over, count how many decimals there are here. How many are there? Just one decimal, right? That means that you'll have 1 followed by 1 0. 7 out of 10. That's how you do that one. I always go back to the original. Here, to go from here to there, I need to divide by 100, right? So you go 12.5 divided by 100, that's 0.125. And here's the kicker. This is a better example for this one. Watch this. Take the decimals, right? 125, write it down. That's your numerator. Over, there are 1, 2, 3 decimal places. So you go 1 followed by 1, 2, 3 zeros. Don't simplify. On a chart like this, I will never make you simplify. You just do it like that, okay? And if you have a ruler, this is where we're going to extend. We're going to add to it. And I'm going to leave that blank there because we did do a bunch of work. And so just 4 more, I think. And then you'll get it. There's an AC on this. Should be prepared. So if you don't have a ruler, just kind of do it by hand and write down the following. 3 over 7, then it's 75.25%, 0.46, and 4 out of 11. So make sure you write those down. I will highlight them to indicate that these are the ones that were there right from the beginning. Right? And if you want to go for it already, go for it, but I will maybe ask you to wait for the first one because that's where the 4 decimals come in. Watch this. Right? You go, some of you are still copying, okay, so I'll wait just a little bit. Okay, so 3 divided by 7, you get this, watch. So that's where you need to round. So it's not that bad. Just count 4 decimal places. 1, 2, 3, 4. You want to cut it right after the 5. What is that 7 going to do to my 5? It's going to bump it up to a 6, right? So it's 4286. 0.4286. 0.86. Leave it on your screen. Leave this on your screen and just multiply that by 100 to get your percentage. And you get 42.86%. So if possible, round your, we used 4 decimals here and 2 decimals for our percentage. Okay. Next, 75.25 divided by 100, right? Because you'll divide it by 100 and you use all decimals there. Like that. Make sure you write this down, okay? And then once you have it as a decimal, you write it like this: 75.25 over, put a 1 down, and then count the decimal places. There are 4. So you just add 4 zeros, and there you have it. And if you're not sure, do this: 75.25 divided by 1 followed by 4 zeros, right? You get back to the decimal, right? So you know you did it right. 46 times 100 is 46%. 46 to a fraction, I will go 46 over 100 because there are 2 decimal places. 4 divided by 11 is 0.3636 because that 3 will not do anything to the 6, so I just keep it as 6. Multiply that by 100, you get 36.36%. So again, I went from here to here, and then I went back to the original to get to there. And I don't know how long you made that line. I kind of went overboard. I'm going to ask you to add something at this bottom here. Remember that the probability in favor of something happening and the probability against that happening, sorry, make sure to write this down, right? Bottom of 145 is always going to be equal to, you can say 100%, or you can say just 1, because they're the same thing, right? Or if you have a fraction, let's say be 14 out of 14, or 7 out of 7, or 200 out of 200, like the rule is that you get 100% if you add them up. And you're thinking, I sort of get it. I need a little bit more, Mr. Dirksen. So here it is. If I told you that the probability of raining tomorrow is 60%, what would be the probability of it not raining? 40, right? So you just knew that if something is happening, then there's a probability of it not happening. And those are called complements. They complement each other. So then it's 40%, right? So combined, you get your 100% under, like you kind of say, under the roof, there's only 100% that you have to deal with, right? Or 1, right? If I said that, let's do another example, probability that you pass the course. If I told you that that's 0.65, what's the probability of not passing as a decimal? It would be, just subtract that from 1, right? If you go 1 minus 0.65, you get 0.35 or 35%, right? So combined to give you 1, right? Another one, probability of winning, the Jets winning. I apologize for this, but you know, that's just what it is. Listen carefully, look carefully. A bar on top of the word is just not, right? Win and not win. So don't let that throw you off. What would be the probability of not winning if I told you that the probability of winning was 1 over 7? 6 over 7, right? So like overall it's 7 out of 7, which is 1, which is 100%. So I need you to understand that something happening and something not happening always adds up to 100%. That's going to be very important for you to understand. It's a concept, and it's a very important concept for that reason. Probability of winning the lottery. This is a good one. Probability of lottery. Let's say it's the HSC lottery. That one is actually not too bad. But let's say there's 1 in 10,000 chances of winning. So 1 in 10,000 win, how many would lose? 9,999 over 10,000, right? Like if one wins, 1 out of 10,000 wins, then the rest will not win the lottery, right? So think of it that way. Chances of winning the lottery are low, yet if you don't buy a ticket, you have 0 chances of winning, right? If you ask me. Okay, I still have half an hour. I need to talk a little bit more yet, but I'm going to ask you to fill in this chart. If I give you an AC and I throw this at you tomorrow, would you be able to fill this in correctly? Okay, so give that a try, and then we'll continue. Okay, so not long. Let's go over them. So 0.89, it would be 89%, because that's all you've got, right? You got to multiply that by 100. And then to go from here to there, you just go 89 over, right? You count 2 decimals, and there you go. Okay. This one, you go 0.67, and then you go 67 over 100, because it's got 2 decimals, right? So in this case, I actually went like this, and then I went like that. Okay. 2 over 37. Let's see how you did with this one. It's a very small number, so you go 0.054, and that 0 turns into a 1, right? So that's 4 decimals there. And then multiply that by 100, you get 5.41%. So you got to be comfortable with small numbers as well. 3 times 100 will give you 3%. And I wonder how you did this one. You count 2 decimals, right? So it's 100 like this, 3 over 100. Okay. You can't cut that 0 because it's not a trailing 0. This is 0.45. You just divide that by 100. And then this gets you 45 over 100. You don't need to reduce those, even though you could. Then 11 over 12 is 0.9167, which gives you 91.67%. Okay, so if you were able to fill this in, you're in good shape. Okay, so this is what you're rounding, and so forth. Okay, now let's start talking about probability and like actually apply probability and come up with probabilities, right? So we'll start with experimental first and foremost, because a lot of the easier examples are like, hey, do you have this bag with candies, right? And what would you get out of it? Marbles, whatever. So experimental probability is what we're going to focus on. And again, experimental probability, right? Experimental probability, it's based on trials, right? It's based on what's actually occurring in the scene, okay? So probability, watch here. Probability, if you have a highlighter or underline, it's a prediction of how likely it is that a particular event will happen, okay? You can express it as a fraction, decimal, percentage, or in words. Okay, that's the one I didn't maybe talk about, but that's easy to do. You'll see the formula to calculate a probability is the probability of that event occurring will be the number of occurrences of the event over the total number of possible outcomes. And at the same time, I will do this. Probability of that event not happening, right? Write this down. Probability of that event not happening, okay? Event A not happening over the total. So both of these are equally important, and you need to always keep them both in mind. Can I just highlight the total? I want to highlight the word total because that is the definition of a probability, to have all the possible outcomes in the denominator. If you don't, then it's not a probability. Okay? Here it is one more time. Experimental probability calculated, right? It's calculated based on measuring the occurrences of A in a sample, right? And find out how many times A occurs. You can make predictions about the likelihood of future occurrences with it. Highlight that too. Predictions. I will also underline predictions, or the fact that you can make predictions. It's very important that you know how to do that. This is on 146. Okay. And here's a formula. This is not going to be found anywhere else, so you got to make sure you write this down. So if you ever need to make a prediction, you take the probability of that event and you multiply it by the larger sample. This is very important. So they might look at Sisler's attendance and they might say that 10% of students miss on a regular basis, just at Sisler. So we have about 2,000 students. That's a pretty good sample size. So the division might say, well, we have 40,000 kids in our schools, 10% of 40,000, right? They'll predict how many would be absent across the division. It's not necessarily accurate, but sometimes that's the best you've got, right? Like when they know how many people died in the Ukraine or how many people are displaced, a lot of that is just like based on a smaller sample. They just assume that's the case for the larger sample, right? Because there's no way of counting them individually. Like when people flee, right? Like you can't count. It's like, hey, wait a minute, let's count before you cross, right? They just cross, right? Like they just want to get out of there into safety. So prediction is very important, though. When there's recalls, you know how they have recalls of food or electronics or cars? The company actually says, well, based on our production here, like 3 out of 100 cars had a defect. So they're like, we sold this many, so we're expecting, you know, this many thousands of cars to come back and be recalled and repaired, right? I mean, if there's a recall, you get to come in and they'll fix whatever is wrong with it for free, right? Just make sure. Did I talk about that vehicle finance? You can type, call a dealer, like if you have like a Honda or whatever, call the dealership, give them your VIN number. You know that long, like every car has a serial number, and they'll tell you if there's any recall ever that happened with that particular car. And so sometimes it's like there's something that catches on fire potentially, like the batteries, something is wrong with it. They will actually, you can bring it in and they will replace it for free. They'll replace that part that causes the issue for free. Just ask them, is there a recall? And they'll actually tell you if somebody has already done it. Like when I bought my Jeep, there were 3 things wrong with it, and they're like all 3 have already been taken care of. They had it on record that they had been replaced, right? So probability comes into this, like it's everywhere. Okay, so let's go to 147 here. This will probably be it. Like this example, I'll do this example, and then we're done for today. So just hang in there. Okay, highlighters ready to go. Georgina bought a bag of bulk candies. She counted them and found that 15 were red, 10 were green, 12 were purple, and 13 were orange. This question basically told you how many there are in total, but they didn't give you the total. They're going to leave it up to you to figure that out. But A is asking, calculate the probability of a randomly chosen candy from a bag being red. Express the probability as a fraction, as a decimal, percentage, and in words. So let's go ahead and do that here. And this is how I state my answer. Probability, I go P of red. Okay, you usually put down what you want, and you know what, you can be creative. Sometimes you can make up your own stuff, own letters. Probability of red, you go, how many red are there? There are 15 reds, right? So you go, there are 15 reds. And this is going to be a little bit, you're not going to do this most likely, but I'm going to go 15 plus 10 plus 12 plus 13. This is the total, right? So out of the total that we're going to get, 15 of them are red. So that's the probability of getting a red on a random draw. So 15 plus 10 plus 12, that's 50. Hold it. Let's say I asked you to simplify this. Can you divide both of them by 5? Yes, I can, right? That would be 3 over 10. And that would be the best answer you could give. This is okay. Can I just say this? Don't simplify if I don't ask you to. And the reason I'm saying that is because sometimes students want to show off and then they get it wrong. And then I have to take marks off. So I would say don't do it unless you have to. And then this as a decimal would be 0.3. As a percentage would be 30%. And in words, you just take the fraction and just say 3 out of 10. Just like that. It's as easy as that. 3 out of 10. So you've stated it as a simplified fraction, decimal, percentage, and in words. That's what they're asking. Would this work if you're peeking into the bag? Is this accurate if you peek? If you're like, let me see, I'm gonna grab, doesn't work, right? It has to be random. It has to be eyes closed. You grab one, and there it is. Okay. So B, calculate the probability of a candy being, the probability of the candy being green or purple. Watch this. This is very important. Or in math stands for add them up. So probability of green or purple. See how I just become creative. Like you don't have to write down the whole thing. There are still 50 there. And out of those, I have 10 greens and I have 12 purples. So that gives me 22 out of 50. So probability of grabbing a green or a purple is 22 out of 50. And I can divide them both by 2. Just hang in there until we're done, okay? 11 out of 25. And that's that. Okay. Then I want that as a decimal. So I go 11 divided by 25. That's 0.44, which gives you, in this case, no rounding necessary. It ends with 2 decimals. Just give me 2 decimals, right? It's only if it's more than that where you need to worry about the 4. And then you would write down 11 out of 25. Could be purple or green or purple. See? Watch this one. This is different. Every single one here is different for a reason. If the distribution of colors in a bag of 1,000 candies, put this down under that larger sample. When they ask you to make a prediction on a larger scale, you effectively are making a prediction based on what you know on the smaller scale. So they're saying if the distribution of colors, if it stays the same, how many would you expect to be red on 1,000, right? So you're making a prediction. So prediction is probability of red in this case times larger sample. So just figure out, we already know what the probability of red is. I'm going to use, watch this folks, I'm not going to use the reduced one. I'm going to use this one just in case I made a mistake, right? Because these are technically the same. So it's 15 over 50 times, what's my sample size? The larger sample is 1,000 candies. I'm projecting it on a larger scale. Okay? When they do polls and figure out who's going to win the election, right? They kind of do the same thing. 15 divided by 50, right? Times 1,000. So that's 300 candies are expected to be expected to be red. And again, you're making a prediction. I just say this. If your answer had been 297.5, you will get half a mark deduction. You need to round it to a whole number, okay? Because we're talking candies, people, votes, something like that. Make sure you round it up. One more. You're like, there isn't anything else, Mr. Dixon. This is the last one. I promise. How many candies would be expected to be orange? Write that down. That's just me adding. How many candies would you expect to be orange? And I like to start with prediction. What's the probability of getting an orange one? You go up there and you say there are 13 orange candies out of a total of 50. I like to put this in brackets like that because that is a probability. And then we're still talking about 1,000 candies, right? So you go 13 divided by 50 times 1,000. That's 260. Expected to be orange. And remember, round to a whole number. I want you to write down the decimal, but then next to it, write down approximately, round up or down. I don't really care as long as you don't state a decimal. Okay, that's it for today, guys. You can handle 7 minutes, right? Other than that, just make